So, hello everyone. Again, my name is Tseng, or you can call me Roy, and I'm from Vision and Learning Lab at National Tsinghua University in Taiwan. My advisor is Professor Tseng sitting over there. So it's my pleasure today to share with you about our work, Nonlocal RoI, on instance segmentation. So let's begin with a simple introduction to our work. What is Nonlocal RoI? The key concept of Nonlocal RoI is to make the prediction on the target ROI by also considering the information from other ROIs. And we apply our method on masked RCN to perform the task of instance segmentation. Masked RCN is proposed as a meta-algorithm to support instance segmentation. Basically, it extends faster RCN with an additional branch to detect the mask for each ROI. The mask branch is in parallel with the existing branch for localization and classification. And different branches share the same underlying features for better speed. The shared high-level feature is extracted by a deep CNN backbone, such as ResNet. And branch networks only focus on a single region of interest when do the detection. So due to this architecture design, masked RCN performs instance segmentation by nature. Besides that, the non-local idea in our work is inspired by a CVPR oral paper this year by Wang and co-authors called Non-Local Neural Networks. They introduce the non-local property into the design of neural networks and present non-local operations as a generic family of building blocks for capturing long-range dependencies, which is very important in CNNs. Basically, non-local operations compute the response at a position as a weighted sum of all the features at all positions. And this position can be a pixel for image data or an audio sample for acoustic data. And for the task of video classification, these positions may come across space-time domain. Let's take this figure for example. The output response at this location x sub I is computed a weighted sum over all the frame here, all the possible position in all the frame here. So the weighted sum is computed across space-time domain. And basically, non-local operations consist of two major parts: a pairwise weighting function f and a unary embedding function g. The pairwise weighting function is used to give a relationship score on all possible pairs of positions. And the embedding function is used to retrieve the features that are used in the weighted sum to ensemble the output non-local response. So here is the general formulation of non-local operations. And as you can see, the output response at a position I is a weighted sum of all the other positions. And the feature is extracted by the function g and weighted by the relationship score output by the function f. And the c of x here is just a normalization factor. And of course, there are many possible instantiations for the this weighting function f. And the Gaussian embedding form written down here is one of the choices. And this is also the one we use in our work. It's worth noting that by using this form of weighting function, the weighted averaging can be easily implemented by a softmax operation. And moreover, this is essentially the self-attention form proposed by the paper called "Attention is All You Need for Machine Translation." So basically, the concept of non-local operations is more generalized than this attention mechanism. And by using this form of weighting function, we can also have the property of self-attention. So why do we need our method, non-local RoI? Before answering this question, let's take a closer look at the typical pipeline of mask RCN framework. This white box represents the shared high-level feature. And region proposal network takes in this feature and gives us the bounding box for region of interest. And then RoI align transform corresponding features according to these boxes into fixed-sized feature blobs, so as to batch these feature blobs into a batch of input and then feed it into the following branches. As you can see here, this number n is represent for number of ROIs. So this makes the prediction independent between ROIs because they only have access to the feature of individual target ROI in the branch networks. So what's the limitation of this kind of per ROI prediction? When you only look at the features within an ROI, the only chance to capture long-range dependencies is through the deep backbone network. However, these high-level features extracted by the deep backbone network are used to propose and detect ROIs at different locations and scales and for different tasks. So it should be generalized to all these varieties. Hence, we argue that the high-level features with large receptive field maybe can give the holistic context about the whole thing, but it's hard for them to contain specific non-local information for different ROIs. Take this image for illustration. When focused on a target ROI, we have a clear context within the region and a holistic but obscure view about the whole thing. And we suggest that it's better to make a prediction while considering other meaningful objects, such as these two people here. And so why not make prediction across ROIs? Basically, we argue that prediction on a target can benefit from the surroundings. And a way to achieve that is through explicitly model the relationships between all ROI pairs. So instead of just looking at the restricted local region, it may be helpful to look around on other regions and then make the prediction. Okay. So the basic intuition about our work is very simple. Let's repeat it again. So prediction on a target ROI should benefit from the information of other ROIs. And we propose to use the non-local operations across different ROIs to achieve that. This figure shows how we apply non-local ROI block to enhance the feature for each ROI. This is just one of the possible implementation of it. Here we just choose to The non-local ROI block takes in the original feature for an ROI and output the non-local feature shows in the blue block here and concatenate it to the end of the original feature block. There are two main contributions for our work. First, we explicitly empower the network to model correlations and attentions between ROIs. Second, and also the difference to the previous work, non-local neural networks, we try to model a higher level relationship between ROIs instead of just between points. An ROI is a set of points and has a higher level semantic meaning as an object. Here is the formulation of non-local ROI. As you can see, the formulation is quite similar to the previous work. The only difference lies in the definition about this x and y. Here, the xi and yi are defined as response at different ROIs instead of response at different positions. And we just adopt the same Gaussian embedding for the implementation of our weighting function. Here's the detailed implementation of our non-local ROI block using this challenge. The orange part corresponds to the implementation for the weighting function f. And there are two embedding functions in Gaussian embedding form. So we use two one-by-one convolutions to implement. The color seems a bit strange. So this part is for the weighting function f. And we use one-by-one convolutions to implement the two embedding functions in the Gaussian embedding form. And also, these two one-by-one convolution will reduce the feature channel dimension for lower computation cost. And for the embedding function g, we designed to embed the feature from each ROI of size d by h d times h times w into a single vector with reduced feature channel. So this is only, there's the spatial dimension of embedded feature is only one by one. Finally, the non-local output response for each ROI is tiled around the spatial dimensions so as to be concatenated back to the original feature block. By the way, the increment of computation cost and number of parameters is not much because we apply the non-local ROI operation on the resized high-level ROI features. Here are some visualizations for the mask and the bounding box on two PT test set images. As you can see, the predicted masks are quite accurate. However, there are many false positives. For example, at this far background area, there are many small false positives. And for a single object, there are multiple highly overlapping predictions. I think these false positives are caused by the fact that our method will propagate the response from ROIs to ROIs. And these false positives maybe can be solved by improving the non-maximal suppression by using the weighting score we have in our non-local ROI block. And we are working on that. And finally, all my implementation is based on my work on this Detetron.pytorch. So all my non-local ROI is based on this implementation. And thank you. This is the end of my talk.
So, thanks for the very interesting presentation. Are there any questions in the audience? Then maybe I have a question. You already mentioned it, that Mascar CNN and also your method usually predicts multiple objects basically for one single object. How could you think of improving the non-maximum suppression using your non-local ROIs?
Okay, so because I think the reason why there are 3 overlapping prediction on this person, and I think the reason why they are there because we propagate this highly confident information from a ROI to another this overlapping ROI. So if we can use the weighting score we have in the weighting function and to choose the one with the most confident and prune the others, and we can suppress this overlapping false positives. Yes.
Any other questions? If not, then let's thank the speaker again. And this brings us to the last presentation today, which is also about